topic of reaction mechanisms really ties together everything from this kinetic section of the class. So here's the key information, which will take some time to go through and work through different examples. The first thing that we need to know about is the reaction mechanism. So in this case, that's the series of steps by which the reaction takes place. So the steps are going to sum to that overall reaction. That's our first key point. Now those steps, what are the individual steps? Well, they're called elementary steps or elementary events. It's a single molecular event, so something like a particle falling apart or two particles colliding, right? Maybe we have A and B here, collide into each other. It's not made up of any other simpler steps, so we have this important takeaway that the rate law can be deduced directly from collision theory. Remember that if A and B collide, we know that the number of collisions per second is proportional to the concentration of A times the concentration of B. So it's just going to be first order in A and first order in B if it is in fact just A colliding with B to give me products. Normally we don't know what those collisions are, but reaction mechanism is the picture of what collisions are actually occurring, so we will know that when we have a reaction mechanism. Okay, the next key point is a reaction intermediate. So that's going to be a substance that's formed and used up during a reaction. We'll see that, again, it's essential for the reaction to occur, and it is predicted or given by the particular reaction mechanism we're thinking about. It's going to typically be less stable. It's only present usually in pretty small amounts during the reaction, but it is a molecule that could in principle be isolated, unlike, say, a transition state. Remember, we have this idea of a reaction progress diagram from earlier in the class. So a intermediate would be something like this, a actual stable molecule at some point along that reaction progress diagram. Transition states are things like this. These little individual peaks on the diagram are our transition states. Okay, so let's start working through some of these examples to see how we can apply those rules. So number one, the steps must sum to the overall reaction. So let's see how that works for this proposed mechanism. So we have a simple example, 2A plus B react to make E and F. Here's the proposed mechanism. A plus B creates C, that's step one. C collides with another molecule of A to give us a D. Then D falls apart into E and F. So again, steps sum to the overall reaction. This is similar to Hess's law type problems from prior chemistry classes, perhaps where we add up the reactions. In this case, we add up all of the reactants here on the left-hand side, all the products on the right-hand side, and then we cancel the things that are in common. So if you look at the left-hand and right-hand side, C and D both cancel out. And then when we add everything up, we get A plus B plus A, so 2A plus B, react, and what's left on the product side is just E and F. That does match our overall reaction up here, so that's just a sign that we've actually written the correct mechanism at all. C and D, again, we can see what happened to those. Those were produced. C was produced in step one and then consumed in step two. D was produced in step two and then consumed in step three. So it's formed, again, in sort of an early step and then used up in a later step in the course of the reaction. That's exactly what it is. So we can identify those as our reaction intermediates. Again, this method of canceling things on each side is usually going to be the easiest way to do it for most purposes. We don't generally need to write out all the reactants and all the products separately. If you just do that canceling using the steps, it'll be a little bit faster. Okay, remember we had a simple collision theory which wrote that the rate of the reaction was related to these three key factors: the fraction of collisions with the correct orientation, the number of collisions per second, and the fraction of collisions with enough energy. Energy of collision E greater than the activation energy EA. So which factor is related to the concentration of reactants? Hopefully you remember that that is the collisions per second. The reason that increase in concentration of reactants increases the rate of the reaction is that more reactants in a certain volume means that we get more collisions and therefore more product being produced. So it's always proportional to the product of the colliding particles, and since in a elementary step we know what collides, the rate law is given right by the step stoichiometry. So the rate law of any elementary step is just some rate constant K times the product of the concentrations of the reactants. And again, in this one case, the coefficient in the elementary step gives the reaction order. So if it's A plus B goes to products, then that's elementary step is first order in A and first order in B, because they each have a coefficient of 1 there. Again, don't try to apply this later, but only for elementary steps. One more key term here is molecularity. That's the number of reactant particles that are colliding in the step. The 3 orders of reaction are unimolecular. So unimolecular has something like A goes to products, and the rate law, because it's just one thing that's, in this case, sort of falling apart, the rate law is just rate is equal to K times the concentration of A. A graphic that shows what that looks like down here is something like this. That single thing just falls apart. For bimolecular now, if we look at that, we have something like A plus B goes to products. Again, the rate law is going to be rate is equal to K times A times B. The coefficients here are 1. There's just one of each particle colliding, so first order in each A and B. Same thing applies if we had 2A going to products. What that really means is that we would have like A colliding with A to form products. So note that for elementary steps, the coefficients really have an important meaning describing the actual collision that's going on. A plus A goes to products is very different than A goes to products. So here's the picture of what that looks like. The 2 particles are going to come in and collide, and again, make products. That's a bimolecular step. Now our final step is termolecular, where A plus B plus C collide to make products. So the rate is equal to K times A times B times C. In this case, the special case would be something like A plus B goes to products, and the rate is equal to K A squared times B. So in this case, it would be quite unlikely for 3 molecules to collide simultaneously. If you look at the sort of picture of what that would look like down here, okay, if we need to have A and B and C collide, think about how unlikely that is for them to collide in just the right way to form the bonds and the products that we need. So that's one of our consequences here, is that in general, while termolecular steps are possible, they're relatively unlikely, and usually our mechanisms are made up of unimolecular and bimolecular steps. Uni for 1, bimolecular for 2, again, termolecular would be for 3. Okay, let's do our first example problem. We've got a reaction mechanism and want to answer the following questions about it. Okay, so A, write the overall balanced equation. This is that step where we add the individual steps. So if I look at this reaction mechanism, I have NO2Cl goes to NO2 plus Cl. If I look here, I've got a Cl being produced, and in step 2, a Cl being consumed. So my overall reaction, when I cancel that out, is 2NO2Cl goes to 2NO2 plus Cl2. That's the overall balanced reaction. The reaction intermediate, so Cl was produced in step 1, consumed in step 2, so that is our reaction intermediate. The rate law for each step, so now this relies on what we learned on the last slide about the molecularity. So rate of step 1 is equal to, this is part C we're doing here, the rate law for each step. That's going to be equal to K1, and the K1 here, right, there. Step 1 has a rate constant. It would be conventional to call it K sub 1, just to refer to that it's step 1. Sometimes we'll write K1 over the arrow there just to highlight that that's the value of the rate constant here. Doesn't make a huge difference, but just keeps track of the fact that now we have rate constants for each individual step. Times NO2Cl. And again, because it's just one particle colliding, just a coefficient of 1, and therefore first order in NO2Cl here. For step 2, same idea. Rate 2 is equal to K2 times, now I have NO2Cl, but it's going to collide with the Cl molecule, so times Cl. The coefficients are each 1, so the orders are for its first order in each of those two reactants. And that's the rate law for each step here. Okay, what does a reaction mechanism tell us about the progress of a reaction? Well, often you can do an experiment to look for those intermediates. We have reactants, and again, as the reaction proceeds, we might go into this intermediate. We have reactants over here, and as we go, we might see maybe this is a two-step mechanism where we form that intermediate, like, for example, that Cl in the last case. That intermediate is very high in energy, present in very low concentrations, but we might be able to detect it using a type of spectroscopy. That could give some credibility to the mechanism. Okay, the next thing we want to do is be able to compare the mechanism and the rate law that it would predict to experiment. The way we're going to do that is using this idea of the rate determining step. So the rate determining step is the slowest step in a reaction. It's also known as the rate limiting step, and sometimes is abbreviated RDS. We can understand that with this analogy with the sand in a, timer type thing here. We've got this pile of sand, and we've got a narrow opening up here. So this narrow opening is what is going to determine the rate that sand falls through the entire system here, through all these bulbs. These large openings later on really don't affect the rate. It doesn't matter if I make this bigger or this one bigger. It's just this first step here, or just in this case, this rate determining step that determines the rate of the overall reaction. So that is always our first approximation, is that the rate is equal to the rate of the rate determining step. Okay, number 1, the elementary steps must add up to the overall balanced equation. The mechanism's rate law, using the fact that the rate of the overall reaction is equal to the rate of the rate determining step must match the experimentally measured rate law. Okay, when we're evaluating mechanisms, we have that first factor that the elementary steps must add up to the overall balanced equation. That's what we've looked at before. Next, we'll be able to compare the mechanism predicted by the rate law to the actual experimental mechanism. So in this case, we'll always use this first approximation that the rate of the overall reaction is equal to the rate of the slow step, or the rate determining step. We'll later on see that there's also this potential equilibrium approximation that we might be able to make in order to compare the experimental rate law to the rate law predicted by a particular mechanism. Two other criteria that are important when doing this in the lab are that we should have reasonable elementary steps. So a term molecular step is relatively unlikely. It's not prohibitive, but if I have other available choices, I should prefer another mechanism over one with the term molecular step. And number 4, if we detect an intermediate not predicted by the mechanism, that would invalidate the mechanism. Okay, so let's look at applying those steps to evaluate the mechanism proposed here for how ozone is produced or consumed, in this case, in the Antarctic ozone hole. We have a little bit of ozone up there. How is it going to be consumed over time? So this is the mechanism in the absence of pollution. We have this proposed mechanism where O3 dissociates into O2 and a free oxygen atom. Then in step 2, the free oxygen atom combines or collides with another O3 to make 2 O2 molecules. The step 1 is that the elementary steps must add up to the overall balanced reaction. So when I look at that, that O is going to cancel, and I will get 2O3 goes to 3O2. That does, in fact, work out. Next, the mechanism's rate law must match experiment. So this is where we have to use that rate determining step idea. So the elementary steps specify the collisions occurring, so we can just use collision theory to write the rate law. So the rate law predicted by this mechanism is, since step 1 is the slow step, the rate law, or the rate of each step, right? We've done that before. So the rate of step 1 is equal to K1 times O3. The rate of step 2 is K2 times O times O3. Now, the last thing that we say here is that, okay, well, rate of the overall reaction is equal to the rate of the rate determining step, which is equal to K1 times O3, because that's the slow step. And does that match experiment? Well, look, experiments show the reaction is first order in O3. That matches. This rate law predicts that it should be first order in O3. So it does match experiment. Next, if we evaluate the other criteria, the elementary steps should be reasonable, so term molecular would be unlikely. There's no term molecular steps here. Step 1 is unimolecular and step 2 is bimolecular, both pretty reasonable. And okay, what about intermediates? Well, in this case, we detect oxygen experimentally using spectroscopy. That's good because oxygen is the intermediate that we predicted here. So this will lend credibility to the mechanism. It wouldn't prove it because we can't ever really prove. There's lots of other mechanisms that could have this same production of oxygen as a intermediate, but this does provide some credibility. And overall, this mechanism is plausible. That's the final best case we can get, is that the mechanism is plausible. We'll never sort of be able to prove with that a mechanism is correct, but we can show that it's plausible. Now, experiment shows the activation energy is large, so therefore the rate is, if you think about it, fast or slow, right? Large activation energy, so the rate on its own is quite slow. And that's why we are able to have that nice ozone layer protecting us from the sun's harmful ultraviolet rays. Refrigerant CFCs catalyze the reaction and therefore increase the reaction rate. Remember, a catalyst decreases the activation energy, making the reaction go faster, and therefore causing the ozone hole. We make this reaction consuming the ozone a lot faster, and therefore we have less ozone in, say, over Antarctica. Okay, the next example here, we'll do another one, sort of evaluating whether this mechanism is plausible. So first we have our proposed mechanism. NO2 plus F2 goes to NO2F plus F, and then NO2 plus F collide to make NO2F, or NO2F again. So first we can add those steps up. There's an F on each side, an F produced in step 1, consumed in F step 2. So that is cancels out, and we do get the correct elementary steps adding up to the overall reaction. Next, the mechanism must correlate with the experimentally observed rate loss. So let's look. Step 1 is the slow step. And so if we look at the rate law for step 1, since step 1 is a bimolecular step, the rate of step 1 is equal to K1 times NO2 times F2. And again, because that's the slow step, we say that the rate of the overall reaction is equal to the rate of the slow step, which is equal to that stuff, and therefore we would predict that rate law for the reaction. So if we compare to experiment shows NO2F times F2, both first order. That's what we see here as well, NO2 times F2, both first order. The steps are each bimolecular, so yeah, the steps are relatively reasonable. Again, we don't have any information about the mechanisms, but if we do know the intermediates. F is our reaction intermediate here, so if we detected that, that would give a bit more credibility to the mechanism. Again, when we think about reaction mechanisms, we now have more information about the activation energy. So in a reaction mechanism, each step has its own transition state or activated complex. In general, that slow step is going to have the largest activation energy. So if we look at this, it's actually no surprise that this is the slow step in the reaction. If we look at what we're doing, we're breaking an FF bond. That isn't the strongest bond, but we are going to have to put energy in to break that FF single bond. So this first step here, where we're breaking a bond, is going to have the highest activation energy. Then we're going to make the sort of high energy intermediate here, that F atom on its own. The next step here is going to be really fast, because if you look at what we're doing here, all we're doing is having that F collide with an NO2, and we're only forming a bond in step 2. So because we're just forming a bond, we're not going to have to put much energy in to cause that reaction to occur. So yeah, the slow step always has the largest activation energy, and bond breaking steps require a lot of energy to put it in, so they are usually the slowest. Okay, some exercises. Take a few minutes to try to do this on your own, and then I'll show the solution. Okay, so we have our reaction. Which mechanisms are plausible? Again, in this part of the class, you will need to explain on the quiz and the exam, so make sure you can generate a good explanation using those 4 potential factors, especially number 1 and 2 all the time. So the first mechanism is sort of the Occam's razor idea of just the simplest possible one. We've got 2 molecules. What if they collide head-on? Well, in that case, we would predict, first, it does match, it is the correct reactants and products, but for what about using criteria number 2? The rate law needs to match experiment. So here we would say the rate for this mechanism here is going to be equal to the rate of step 1 is equal to K1 times NO2 times CO. But that doesn't match experiment. The experimental rate law is that it's second order in NO2 and 0 order in CO. So this doesn't match experiment, and so this is not possible because of that violation, because this rate law, first order in each reactant, doesn't match experiment. Experiment showed that it's actually second order in NO2 and 0th order in CO. Okay, what about possible mechanism B? So you've got to evaluate each criteria. Number 1, does this actually add up to the correct products? Well, NO2 plus NO2 goes to NO3 plus NO. NO3 here, we can cancel out. And we get NO2 is here. We can see, look at this. NO2 came here. It was produced, it was used up first as a reactant and then consumed as a product later. We'll see that that's actually what a catalyst does in a mechanism. So this is sort of an autocatalytic type reaction. NO2 acts as a reactant and a catalyst. That's possible and happens in several types of mechanisms. The final answer here, NO2 plus CO, goes to NO plus CO2, does match the actual reactants and products. Now, does the rate law match experiment? Well, rate here is going to be equal to the rate of the slow step, which is just step 1, which is equal to K1 NO2 squared. Because there's 2 NO colliding, it's NO2 times NO2, or NO2 squared. Again, the coefficient here of 2, there's 2 NO2 colliding, matches the exponent here, and therefore it is at least plausible or consistent with experiment. We can go to the next factor, number 3. There are no termolecular steps here. These are both bimolecular. We don't have any information about intermediates, but if we did, we could use that in further evaluating these mechanisms. Next, let's look at the case where we have a more complex reaction mechanism that makes it a little bit more difficult to compare the rate law to experiment. In our case, we're going to focus on mechanisms where there might be a fast initial step that could reach equilibrium. So let's look at this example. 2 NO react with O2 to make 2 NO2 molecules as the products. And we have the experimental rate law is KNO2 NO squared times O2. Here's a proposed mechanism, is that first 1 NO molecule collides with O2 and goes to NO3. In this mechanism, this is a fast step that is reversible. So it goes in both the forward direction and in the reverse direction, unlike the steps we've looked at so far. NO3 can sort of fall apart back into the NO and O2. Then a second step is our slow step. NO3 collides with another NO to make 2 NO2 molecules. So that's our slow step. Now let's try to figure out the rate law. Well, again, as before, we always start with the idea that the rate of the overall reaction is equal to the rate of the slow step, or the rating step. So the rate of the overall reaction is equal to the rate of step 2, our slow step. And then we look and we can say, okay, the rate of step 2 is K2 times NO3 times N. Now let's try to compare that to experiment. So in this case, we run into a bit of a problem. If I look at the experimental rate law is second order in NO and first order in O2. When I look at my rate law down here predicted by the mechanism, I have first order NO and first order in NO3. But NO3 doesn't show up in this reaction. It doesn't show up in the experimental rate law. NO3, remember, is an intermediate. If I look back at my mechanism there, NO3 is an intermediate. And so the problem is that reaction intermediates are not something we measure and control in the lab. So we don't have them in our experimental rate laws. So what we need to do is take this NO3 and find a way to write the concentration of NO3 in terms of the things that we can measure in the lab. NO, O2, even NO2, the concentration of product, we could write. So how can we write the concentration of NO3 in terms of the concentrations of our reactants and products? In general, there's several ways involving different sorts of approximations we can make. In this class, we'll just look at, so our approach in this class is we're going to assume that this fast step is much, much faster than this second slow step. And so we can assume that it reaches equilibrium very quickly and that step 1 is always at equilibrium throughout this entire reaction. When we're at equilibrium, we have this important fact that at equilibrium, the concentration isn't changing, and that's because the rate of the forward reaction and the rate of the reverse reaction are exactly equal. So then what we do is we say, okay, our fast equilibrium step here is step 1. So we're going to say rate 1 in the forward direction is equal to rate 1 in the reverse direction. Then we can plug in rate 1 in the forward direction. Again, it's an elementary step, so we just write that that's going to be K1 and then NO times O2 using the coefficients. And then for the reverse step, what do we have to do? Well, we just think about this reaction in the reverse direction. In the reverse direction, we have K minus 1 is the rate constant, and the reactants in the reverse direction are, the products in the forward direction. So again, when we're thinking about this, we're thinking about NO3 turning back into O2 and NO with a rate constant of K minus 1. Again, we could sort of flip it and write it normal left to right, but you don't have to. You can just look at the product and see what the reverse reaction is. So again, this will have a rate constant of K minus 1 and then just first order in NO3. Now what we want to do here is now we'll be able to solve for NO3. Remember, that was the problem, was that we didn't know what the concentration of NO3 is, but under this approximation, we can just solve for NO3, the intermediate. We do that by just dividing both sides by K minus 1 to get NO3 by itself. Now we have this expression for NO3, and remember the slow step, we had rate is equal to rate of step 2, which was K2 times NO3 times NO. And so now we can plug that back in. We know that the concentration of NO3 is equal to all this stuff, so we plug that in, and we can now say that the overall rate of the reaction is equal to K2 times K1 over K minus 1, NO times O2, all times our NO still. Now we've achieved our goal. There's no longer any reaction intermediates, and so now we can compare this to experiment. We could see that directly, but it's convenient to sort of bring all like terms together. So there's a bunch of rate constants. Those three we can write as either one big rate constant, or again, for now, I'll maybe just leave them as a bunch of individual rate constants, but you could wrap those up into one big K. And then if we look at the terms here, we have NO times O2 times NO. So we have NO times NO, which is NO squared. So NO squared times O2. And if we compare that back to experiment, we do have a match. The experimental rate law, I removed it from this slide, but the experimental rate law was second order in NO, and first order in O2. This just shows that same set of math that I did on the slide before with nice typesetting and formatting, showing that everything matches as well. So this is the other type of rate law that we can determine, is where we have these fast initial steps, a little bit more math and work, but then you can still get a good comparison to experiment and go, do the rest of the problem in the same way. Okay, so our next example, see if you can identify the intermediates and determine if the mechanism is consistent with experiment. Okay, first, reaction intermediates. That's really a part of that step 1 where we generally try to add up all the steps. So if we do that here, we see N2O2. I'll go back to a better color here, maybe red. N2O2 is produced and then consumed, so that's an intermediate. N2O is produced and then consumed. I don't see anything else here that's canceling, and so our intermediates are N2O2 and N2O. Okay, for part B, the first step is just to check that we have the proper reaction, so 2NO plus 2H2 goes to N2 plus 2H2O, and that does match up above. Next, we have to do the step of comparing the rate law to experiment. So for that, again, we always start in the same place. We're going to say that the rate of the reaction is equal to the rate of the slow step. In this case, the slow step is step 2. So that means that this is going to be equal to the slow step, which is K2 times N2O2 times H2. Elementary steps, we can determine the orders just from the coefficients, just from the stoichiometry. Now we look at that and see, okay, can we compare directly to experiment? No, not yet. The problem is that we have that intermediate. So we have N2O2 as one of our intermediates, and that's not going to show up in an experimental rate law. So what we need to do is find the concentration of N2O2 in terms of our other reactants. In this case, we can do that by using our fast equilibrium approximation. So we'll do that part of it. We'll assume step 1 is at equilibrium. So that means, again, what equilibrium means is forward and reverse reactions have the same rate. So rate 1 forward is rate 1 reverse. Now we plug in. The forward reaction has a rate constant of K1 times there's 2 NO particles colliding. So that's going to be NO squared as the order, because there's 2 particles colliding. And then the reverse reaction is K minus 1 is what we'd use for this reverse reaction. And now the reactant is what would have been the product in the forward direction. So it's N2O2 is the reactant. And there's just one of them, so just a coefficient of 1, or just an order of 1 is the exponent there. Now, remember, the next thing we would do is that the whole problem was that we needed to write N2O2 in terms of things that we can actually measure in the lab. So that's what we want to do. We want to solve for N2O2. We do that by just dividing both sides by K minus 1 to get N2O2 by itself. Now we have an expression for N2O2. It's K1 times NO squared divided by K minus 1. We also, again, since that's NO2, we can plug this back in for N2O2. That's always the last step, is we take the new equation for the intermediate and we plug it back into the slow step. So let's do that. I'll just write it up here on the line I was on before for the sake of space. So now the slow step is equal to K2 times N2O2. I'm going to plug in my new expression, K1 over K minus 1 times NO, the whole quantity squared. And then I still have what's left, the H2 outside. Now, again, I could make this a little bit prettier. Rate is equal to some new rate constant K times NO squared times H2. where this overall rate constant K is K2 times K1 over K minus 1, but I can now compare to experiment. NO squared, so second order in NO, that matches, and first order in H2, that matches. Last couple types of things to see if it's consistent with experiment. Are there any termolecular steps? No, all bimolecular here in the forward direction. Again, doesn't give us any information about intermediates, but we could use that as well. So again, our final answer here, because the rate law matches, because the equation matches, yes, it's going to be consistent and therefore sort of a plausible mechanism. Okay, the next part of this exercise, take a minute to look at these. Okay, the solution. Are either of these mechanisms consistent with experiment? So mechanism number 2 has this slow step. In this case, again, I could always do the step of adding all the equations up. I should always do that. In this case, though, right, if there's any problem with the mechanism, I can invalidate it. So here I can say that the rate should be equal to the rate of the slow step is equal to the rate of, in this case, it's just sort of step 1 is the slow step. So we would say that the rate should be equal to K1 times H2 times NO. There's no intermediates or anything in there. It's just that first step, and that does not match experiment. We predict by this mechanism first order in NO. Experimentally, we observe it second order in NO. So no, not consistent with experiment. Okay, what about the next part? Well, for mechanism 3, we can do that same analysis. Rate is equal to the slow step, which is just step 1 in this case, H2 times 2NO. So that would predict a rate law of K1 times H2 times NO squared. That does match experiment, so that part of it is good. The next part, we should check that everything adds up correctly. So if we look N2O, cancels, and no other intermediates. When I cancel my N2O, I can see that my overall reaction is 2H2 plus 2NO goes to N2 plus 2H2O, which is the correct overall reaction. So yes, it would be sort of a plausible mechanism. It is consistent with experiment. When we look at it further in part B here, well, which one is going to be the most credible? We do have in mechanism 3 this termolecular step, 3 particles colliding. That's slightly less likely. It's possible, but generally unlikely. So maybe mechanism 1 is the most likely, considering all of our evidence and looking at that unlikely termolecular step. Mechanism 3 isn't ruled out by any means, but mechanism 1 is probably a little bit more plausible because it lacks that termolecular step. It has all reasonable steps. Okay, the last set of information on this reaction mechanism content is about catalysts. So in simple collision theory, we talked about catalysts and their properties. They increase the rate of reaction without being consumed. The way they do that is by lowering the activation energy, which is increasing the rate of both the forward and reverse reaction. We don't ever change the product that we get, we just form it more quickly. And therefore we have sort of a different reaction mechanism. The catalyst will enter the rate law before the rate determining step and then get regenerated later. Now, here's an example. We have an uncatalyzed reaction. A and B collide to make the product. This is relatively slow. When we add a catalyst, A and the catalyst can collide to make some intermediate C. Then C reacts with B to make product. Now this first step is, relatively faster than the step here, but of the 2 steps here, the first one here is our slow step. This second step is really, really fast, and it does show what we just expected there. The catalyst participates in the mechanism, but it gets regenerated later. So notice how this differs from an intermediate. So the way a catalyst works is we have the catalyst, it shows up here as a reactant. First it's a reactant on the left-hand side, then later it gets regenerated as a product on the right-hand side. Whereas an intermediate is just generated in the course of the reaction by default, a catalyst, we had to explicitly add this to the reaction mixture. So we know it's there, we can control its concentration. It's actually perfectly fine for it to be in the rate law, and it sort of has to be in the rate law in some fashion, or even if it's zero order, just because it does affect the rate. This is what that looks like on our reaction coordinate diagram. Again, a catalyst lowers the activation energy, so before we had this one-step pathway with a large activation energy. Now, in the second mechanism, we have a slow step. So this first step is the slow step, so that's why it has a bit higher activation energy. Then we make our intermediate. Then the second step is really fast. The second step is very low activation energy. So that's what's happening here. Catalyst is stabilizing the transition state and therefore speeding up the rate of the overall reaction. Okay, so when we analyze this example mechanism, what is the reaction intermediate? Well, if I look at it, again, my reaction intermediate was produced and then consumed. So C fits the definition of a reaction intermediate. What is the rate law? Well, the rate law comes from the slow step. That's not any different. So we would say the rate is equal to the rate of the slow step, which is rate 1, which is K1 times A times the catalyst. Again, perfectly fine for the catalyst to show up in the rate law. That is sort of what we expect. Okay, so here's our summary about reaction mechanism content. I think this last one is really important. They allow us to understand how things are formed, prevent unwanted byproducts, and allow us to develop new compounds. We might want to catalyze certain reactions or slow down other ones. That's all going to be related to these reaction mechanisms. Again, some other key terminology here. We had our mechanism, elementary steps, molecularities, so unimolecular, bimolecular, and termolecular, where again we can just get the rate law right from collision theory. Reaction intermediates and catalysts are things that cancel out of the overall reaction, but are very important and work a little bit differently. Intermediates are formed as products, then used up as reactants later. Catalysts we add to the reaction mixture, so they're going to be used as a reactant on the left-hand side first, then later regenerated as a product. Again, you have to be able to do this comparison between the rate law and the mechanism. So we always apply the same procedure. We always start with comparing the slow step to the, or saying the rate of the slow step is equal to the rate of the overall reaction. Then if we have intermediates in the rate law, that's the case where those don't appear in the experimental rate law. So we have to solve for those intermediates using that fast equilibrium approximation, plug back in, and then we'll be able to make our comparison.